talk you through knots and how to distinguish them.
Thank you. It's a pleasure to be here, and I must say it's really wonderful to see so many people here. 7 o'clock in the evening after all the lectures and so on. So, as I said, my title is Knots and How to Distinguish Them, which I guess is a slightly enhanced version of when is a knot, not a knot. Okay, so I'll start from the beginning. Knots, well, they have a history going back to ancient times. The way ancient knots, Celtic knots, knots that sailors use, fishing knots, making nets, even knots for rope climbing. So if you look in a book about such things, and some of the simplest knots, this is called a figure-8 knot. So, and the granny knot will be drawn. So, figure-8 knot, turn your head, you see some sort of an 8 here. Granny knot, well, not by mathematicians. So the first thing, as far as usefulness is concerned, if you want to use it for rope climbing, you want it not to slip. Okay, so the importance as far as applications go in that way is whether it slips, whether it doesn't. And that depends on the thickness of the knot. As soon as we move to a mathematical model of it, then we're going to assume that the curves are of 0 thickness. And of course, if they're of 0 thickness, everything can slip out. Anything you can tie, you can untie, so you have no knots left. So in order to actually make something that is a knot, we're going to tie the ends together. So for example, the mathematical version of a figure-8 knot would look something like so. So as it's 8 in it, so this would be the mathematical figure-8 knot, and we'll meet the granny knot a bit later. Assumingly will be a closed knot. So, yes, so as I said, the history of knots goes back to ancient times. Lots of things you can look at knots, you can look at their symmetries. Sometime in the 18th century, Van der Mon started studying knots in a more rigorous mathematical way. Gauss, as usual, was one of the first to really try and do something interesting with them. In the 18th century, student listing was started trying to make tables of knots. And then it was impetus from physics, trying to make models of atoms. There was something called the vortex theory of atoms, which Thomson was trying to make, together with Maxwell and Tate. So this is Kelvin, James Clerk Maxwell. The vortex theory of atoms. And the idea was that atoms, this was sometime in the 1860s, the atoms are some sort of motion of the ether which has a singularity, and the type of singularity should correspond to the type of atom. So he thought the singularity is rather like if you look at smoke rings moving, and then, so these rings can be knotted in some way. So he thought these singularities could be modelled by knots. So the first thing to do is to work out how many knots there are. So he sent P.J. Tate off to start making knot tables, and he did that. He got to tables, in fact, of 10 knots. Sometime in the late 1870s, he published these tables, which were mainly accurate. There were some errors in them, there were some things missing. So he really started the classification of knots. Okay, so let's go back to the beginning, which is what is a knot? So we're going to be talking about knots in 3 dimensions. of, as we've said, it's going to be a zero thickness curve, so it will be embedding of a loop and a circle in R3. It should be something continuous, of course, and something which doesn't intersect itself. So S1 I've just been in circle. So you can give it a circle, let's say. So numbers with modulus 1. So mapping to R3, or you can parameterize it. How you would parameterize complex numbers with modulus 1 most simply. E to the
2 pi pi k.
right, e to the I theta. So if you use e to the I theta, then theta will go from 0 to 2 pi. So like mathematicians say, you ask them how long is a piece of string, they say 2 pi. So you can have a parameterization, say, like so. So you want to map with r of 0 equal to r of 2 pi, the n is pi, you want it to be continuous, and you want it to be injected, well, apart from the end, so you want this map to be injected. Okay, so in other words, it doesn't cross itself. Okay, so that's a definition of a knot. So that means that we need to give 3 coordinates as functions of theta in this case. So for example, here's an example. Theta goes to 2 plus cosine 3 theta. Cosine 2 theta. 2 plus cosine 3 theta. Sine 2 theta. And minus sine 3 theta. Okay, it's continuous. It's going to take you all along to check it's injective. What on earth does it look like? Well, so in this particular case, we can figure it out pretty simply. Well, so if you look in the xy plane, you see you have a constant times cosine 2 theta, constant function, I should say, times sine 2 theta. So in other words, in the xy plane, this will be a point with polar coordinates. The radius is. Yeah, so the radius will be 2 plus. The radius will be 2 plus cosine 3 theta, and the angle will be 2 theta. Okay, so it will be somewhere at an angle of 2 theta, and at this radius. Well, what does this function do? It bobs in and out between 1 and 3. Okay, so it will be something bobbing in and out between 1 and 3. And when theta goes between 0 and 2 pi, how many times will it go around? Twice. Okay, good. Okay, so that's what it looks like from on top somehow. It's bobbing in and out, in fact, 3 times, because there's a 3 theta here, and it goes around twice. Then it comes back to the beginning. Okay, let's try and see what that means a little bit more accurately. So there's something that we're rotating around the z-axis by 2 theta. Well, what is this? If we look in the xz plane, the radius is this 2 point whose x-coordinate, the radius is 2 plus cosine 3 theta, and the y and z coordinate, it's said, in the xz plane, is minus sine 3 theta. What will this trace out when theta varies? So if I moved the 2, it would be a circle of radius 1. So it would be a circle of radius 1, because the minus sign will be going clockwise instead of anti-clockwise. But because the 2 is shifted to the right, so it will be going around a circle like this, it goes 3 times around the circle. Now, while it's going 3 times around the circle, we just saw that we're going to have to twist it round so it's going twice. We take this and we rotate it around the z-axis, and it's going to go twice all the way around as theta goes from 0 to 2 pi. Okay, so what are we going to get? So, well, with a bit of imagination, you might persuade yourself that what you get is this. So here's the z-axis coming down, and here's your point which is rotating 3 times around while you go around the z-axis twice. Okay, so anyway, this is a way of presenting the trefoil. But if we had to present all our knots by analytic expressions of this form, then we wouldn't manage to get very far. So, yes?
Would
change the numbers 2 and 3 to any numbers, well, we should co-prime in fact already. Something else. And those are called, if you change them, instead of being 2 and 3, if you change them to m and n, then you get what's called a torus knot. And they live on the torus because if you take the surface of revolution of the circle, then you'll get a torus. Yes?
Is the orientation part of the definition?
Yes, okay, good question. So indeed, theta is increasing, as theta increases from 0 to 2 pi, then that will give you an orientation. So yes, there is a piece of information which is important, as we'll see, which is the orientation, yes. This trefoil, if you take the trefoil and turn it round, not reflect it, but just turn it round through pi, rotate it around some axis here, then this arrow will go the other way round. And if you look at it, you may think at first that the orientation of the trefoil will change, but it won't. Yes? If you start with it here like this, and you turn it round, you'll still find that you have the same orientation for the crossings, but the orientation of the knot will have changed. But it's not true that for every knot it is equivalent to a knot with the opposite orientation. Yes. Okay, so, all right, so that's a knot. But what about equivalence of knots? We obviously would like to be able to identify knots and recognize knots, so we'd like to know when two knots may be the same. If we distort it slightly or turn it around or even just take a piece and push it in another part, we'd like to still say it's the same knot. So how can we define mathematically equivalence of knots? So what we'd like to be able to say is that two knots are equivalent if you can move one to the other without cutting or gluing in a smooth way, or at least in a continuous way, and in such a way, of course, that you didn't pass the knot through itself. So at every stage, every time, you still have a knot. So if you take that idea, this is equivalent knots. So if you take the definition, which is to be able to deform one to the other without cutting or gluing, well, the mathematical notion that correspond to this would be you need a further parameter. So let's say we've got R of S T. This is our theta before theta. This is the parameter on the knot. This is a further parameter, the deformation parameter. So we've now got a function of two variables. For each value of S, we have a function of theta, which will give a knot. And we would like this to be a function of an element of R3. And we would like it to be continuous. So you might think that the conditions would be like this, that R should be continuous, that R for any particular S as a function of theta will be a knot, in other words, be injective. Self-intersecting. That R, well, of course the ends have to be closed. And at the beginning of time, when S is 0, that this represents your initial knot, and at the end of time 1, say, that this represents the knot you want to go to. So this is a way of conceptualizing. S is time, going from 0 to 1, conceptualizing the idea of deforming continuously one knot to another. Unfortunately, as we'll see, it doesn't work. It doesn't work because you take a knot, this, let's take a knot, and then let's pull it tighter and tighter. So this, we're going to stretch out you can do that in a way which is continuous. So maybe we do it the other direction. We'll say that the size here will be t. So when t is 1, it will be a certain size. T is a half, it will be half the size. T is 0, will disappear. We'll take a particular piece of it and just shrink it and leave the rest exactly the same. So t is 0, this will have disappeared, and we now have the unknown. Well, obviously that wasn't a good definition, because by that definition the unknown will be equivalent to every time. Okay, so we have to think again. And the correct notion is what's called ambient isotopy. So that means you think of the knot as sitting in space. We forgot about the rest of space, essentially. We were just deforming the knot. You think about it sitting in space and require that you move the whole of space. On top of honey. So as you're moving the knot around, everything around it is also moving. And you require to do that in such a way that at no point does a piece of space disappear. So it has to be what's called a homeomorphism, a continuous inverse. Then you open the definition of equivalence of knots. So the correct definition is what's called ambient isotopy. Equivalence. So then you'll say that K0 is equivalent to K1, these are two knots. If there exists an ambient isotopy, H01 cross R3 to R3, such that at any time, H at the time, which is now a map from R3 to R3, is a homeomorphism, and H at time 0, so at time 0, the space is where it is, so it does nothing at all. It will just be the identity map. And H at time 1 will take one knot to the other knot. So it will take one knot, K0 theta, and K1. So instead of just deforming the knot, we're finding a way of going from the honey being fixed to the honey moving one knot into the other knot. Okay, so that's now a firm mathematical definition, but rather like this,
Question.
it's not very useful. Yes.
This is the orientation.
Well, it will have to, won't it, because the initial one did. So
Sorry.
this one was the identity. But you're right. I mean, I could put in the condition it preserves orientation. Since H is 0,
Oh, yeah,
H,
sure.
so it really needs the identity. But yes, you're right. And yes, that's a good question, because so now we have two orientations. We have the orientation of R3, and we have the orientation on the knot. And they're both interesting. So if I change the orientation of R3, it means taking the mirror image. And if I change the orientation of the knot, it means changing the arrow. So the mirror image of this will be this. Think of it as reflecting in the plane of the board. And in fact, well, what do you think? Do you think these are equivalent? No. So this is normally called the right-handed trefoil, this is the left-handed trefoil. But not all knots are like that. Are an equivalent to the mirror image. For example, the figure 8 knot, which I drew at the beginning, is equivalent to its mirror images. Okay, so as I said, the trouble with this definition, it is a very watertight definition, but it's not very useful. How would I ever tell whether the two knots were equivalent by this definition?
Next question.
Yes.
So, since they're mirror images of one another, should the right-handed and left-handed trefoil be going both clockwise with that, or should
No, you see, yes, I took a mirror image in the plane of the blackboard. So the arrow was the same way. But as I said, actually, as I said before, when there was a question about changing the orientation, if I turn over, not the mirror, just rotate it through pi, then this arrow will go the other way. So actually this is equivalent to the other direction, so there's no reason to leave the arrow on. You're right. Yes. Yes.
So is it obvious that like So you described something where you like continuously made this knot tighter and tighter, so it gets arbitrarily small, I guess. And then
Yes.
disappears.
Yes.
Is it obvious that if you do the thing with the honey, that the same problem won't occur?
No, it's not obvious. I mean, yeah, you're right, yes. I mean, the problem is now we've got a nice definition, but how are we ever going to tell if two knots are equivalent? So, you're right. I mean, if they are equivalent, we might be able to build a map between them, but if they aren't, how can we prove it? Yeah, so the one more little problem, which is there are things called wild knots. So, a wild knot is something you could make, for example, would be something like this. So, you could take a knot, a piece of knot like this piece, say size 1, then we'll take something at half size, and then we'll take something at quarter size, and so on. And you could build that in such a way that it's a continuous map. In other words, it's a knot. Okay, so there will be a limiting point somewhere, but it doesn't really matter if it's not. So this is called a wild knot, and we don't want to discuss such things. So in order to limit the discussion to something that's tractable, we define a tame knot to be a knot that's equivalent, means ambient isotopy equivalent, to a piecewise linear knot. A piecewise linear knot is one such that the map that defines it is piecewise linear. Tame knot is, by definition, ambient isotopy equivalent to a PL knot. So that just means, geometrically, made out of sticks. Yes? So, well, nothing more interesting. Use this. I'll say friend again. Yeah. So this is the trefoil again. And you can see that you can make it out of 6 sticks. You might wonder if you could make it out of fewer, and the answer is no. This is the stick number, and actually there's a theorem which says that the stick number for a torus knot, for any torus knot, the stick number, well, is 2n if m is less than n is less than 2n. Okay. So anyway, we're requiring that the knot can be represented with a finite number of segments, although we won't usually draw them that way. Okay, so now we can ask the question, how many knots are there? Well, it's fairly easy to see that it's uncountable. Well, it's not that easy, but it will be. Yeah, I mean, it's infinite. It will be countable, in fact. Sorry. And then you can try and make tables. So how are you going to represent knots? Well, obviously not by analytic functions, but by pictures like we've been doing on the board, projections, not diagrams. So once you know that all your knots are going to now emit the adjective tame, and similarly ambient isotopy will just say knot, when we mean tame knot, and equivalent when we mean ambient isotopy equivalent. Since all the knots in our world are equivalent to PL knots, you can take a PL knot, sticks in R3, and project them onto the plane in such a way they're in general position. General position means that the diagram is clear. So to be precise, it means that you don't see a corner and another edge in the same place. You don't see, of course, 2 crossings. And you don't see 3 crossings, the same 3 lines crossing at the same point. So if you disallow anything like this, then you will call it projecting into a plane in general position. Then you will have, take literally PL knot, then you will have a diagram like we had there. It will have straight line segments, and it will have crossings with each crossing over and under marked. So we don't usually actually draw the straight line segments, but you can think of it as a graph, 4-valent graph with extra information at each crossing, which segment is going over. So that is a knot diagram. Okay, so now we've got away from analytic expressions for functions that give you the coordinates to instead having diagrams. That's a little bit better. But now, what about the equivalence? The equivalence is ambient isotopy equivalence. How are we going to represent that in terms of diagrams? Certainly not many diagrams, but they're not. So that's where something called Reidemeister moves comes in. So we're now working with something combinatorial, these not diagrams. And Reidemeister moves, they tell you precisely when two not diagrams are equivalent, or at least what moves you might be able to perform, which will retain the same knot. And these moves are as follows. So if you have a little piece of knot which has a twist in it, you see I'm already not drawing them as segments, line segments, but then I can do this. This is called type 1 move. Type 2 move is called the tongue. That's if you have tongue sticking over like this, then you can slide them apart or the other way. If they're like this, you can move it back again. And the third move is called a slide. And that says that if you have a crossing, and you have another piece going down here, then you can move this piece underneath over here. They're all pretty obvious moves to make. Clearly they don't change the knot. What's not so clear, it also isn't so difficult to see, that these moves generate the equivalence of knots that was defined by ambient isotopy. In other words, any two knot diagrams which represent the same knot can be moved from one to the other by these moves. And if you want to work out how you would think about that, well, you think about it in terms of the PL knots. You try and think about what will happen when it's moving around, and what changes can possibly occur to the diagram. A change can only occur if you pass through a place which is not in general position. A place is not in general position where the types that I drew at the beginning. So then you start working out what happens if one of these things happens. So this is like a tongue, this is like a slide. Well, I guess it's sort of like a tongue. And similarly, yes, you can get something else where two curves on the same, two lines are exactly in line. And I guess that would correspond to undoing a twist. Okay, so now we reduce the problem to looking at not diagrams up to these moves, which is still difficult. Well, at the moment, these moves are really useful if you want to explain to your friend why two diagrams are equivalent, and you don't want to just tell them to take a piece of string and make it and wiggle it around and it will work. Okay, so you actually write down a proof now. If you had two diagrams, you could write down the steps one by one, and at the end you would really have proved that the two were equivalent diagrams. You couldn't prove, though, that two diagrams are equivalent that way, at least not directly. Maybe you just didn't find a path from one to the other. So, you might think that going between two equivalent diagrams is fairly simple. For example, suppose I want to know if a knot is the unknot. So you might think, well, if it's the unknot, you're going to sort of use these moves, so you can untie. So here's an example of a knot. A minute. So it is. Okay, so it appears to have 10 crossings. If you look at it a bit, you might be able to work out that it's really the unknot. Yeah? Okay, so, well, it is actually the unknot, but it's a rather nasty unknot. At least a rather nasty unknot representation, because there's no simplifying move of type. Move of type 1, or type 1 or 2, and there's no move of type 3 that you can apply. apply here. I mean, if you look at it, then, well, for a move of type 3, you have to have the right configuration, and there are no loops that I can suddenly undo, and there are no tongues, all these things that look like their tongues actually, well, they aren't quite, they have the wrong orientation. So this is a diagram which has 10 crossings, and they say it is actually unknot. So the easiest way to know is find out if the unknot is taken as a string, I think at this point. But if you want to apply Reichenmeister moves to this diagram to get to the unknot, then the minimum of the maximum number of crossings in the path is 12. You have to make the diagram more complicated. There's no simplified move. There's no move of type 3. What does that mean? That the only moves you have to do at the beginning will be moves that are more complicated. A little move either this direction, this direction. In fact, you have to put 2 additional crossings in before you can simplify. So that illustrates that there isn't going to be a simple algorithm for looking at a knot diagram and determining whether it's the unknot by using these moves. Not this matter. Okay, so how are we going to determine, say, if a knot is the unknot? Well, we need invariants. What are invariants? They're things which we can define somehow, and we can evaluate, and we know that they will be unchanged under Reichenmeister moves, and that would mean it's an invariant. And if we see that the evaluation on 2 knots is different, then we know it's impossible to get from one to the other. So that's the big news. There. Okay, so what invariants? For example, well, what sort of invariants can we think of knots? We can think of the crossing number, which is the minimum number of crossings, stick number, unknotting number. Unknotting number is the smallest number of times you have to pass a knot through itself for it to unknot. So for example, well, this is already unknotted, but if I took something else, so if I change this crossing to the opposite crossing, yes, if I just change this crossing, then it's already an unknot. It's already back straight and forward. So the smallest number of crossing types to change is called the unknotting number. The trouble with all these definitions, then they're easy to define, but they're hard to calculate because, again, you don't know when something is the unknot and when it isn't, so they're pretty useless to identify knots. So, to give an example of something which is useful, the easiest one is to go to links. So links are just like knots, except we have several components. I won't go through all the definitions, but it's exactly the same. So we have several circles that are non-intersecting, embedded in R3. So I'll tell you about the linking number. So this is gas.
It is nicer.
I see there's a wonderful book here.
You can use this if you want.
Okay, yes. Thank you. Okay, so let's just draw something simple. Here, and then the other one will be straightforward. Okay, so we've got a 2-component link, and we want to know the linking number. So here is one definition. First definition will be like this. So let's call this component number 1, this component number 2, and now we'll only look where component number 2 goes over component number 1. Okay, so to make this work, we need to choose some orientations on the 2. So pick some orientation. number 2 is going up, well, only look where component 2 goes over component 1. Okay, so if it's going over, component 1 is going under, it's either going from right to left, or it's going from left to right. So we'll call this positive, we'll call this negative, or let's say we'll give this a contribution, it will give a contribution of +1, this will give a contribution of -1, we'll take the sum of all the contributions, and that will be the definition of the linking number. Okay, so that's a definition. How does it work out here? So we have 2, so we want to know only where 2 goes over 1. 2 goes over 1, so it's coming out here, up. So it goes over 1 here, yeah. It goes over 1 here, and it goes over 1 there. So now we have to see what the signs are. This was coming down here, so this is going this way, but it comes from right to left, then it goes round, it goes again, right to left, and then it goes. So the linking number is
3.
3. Okay. Okay, and you can see that that it's strongly dependent on orientation. So for example, if I let K prime be K with the opposite orientation, arrow, okay, then the linking number so I have 2 components, K1 and K2, K1 prime and K2 will be minus the linking number of K1 and K2. Okay? And if I put them both in the mirror, then the linking number would, I think it will reverse. If I swap the 2 round, well, think about it. I won't tell you the answer now. If I, instead of taking linking number of K1 and K2, I take the linking number of K2 and K1. Okay, so think about that. We'll come back to that in a moment. Okay, so I've written out a definition, but I could have written all sorts of things. I could have written, for example, that I'm only going to count when component 2 goes over component 1, and say this goes from, component 1 goes from right to left. I won't count these at all. Would that be a viable thing to do? Well, of course I can write all sorts of things, but I have to check it's invariant. How do we check it's invariant? Well, we check that under the Reidemeister moves, it's unchanged. So, what happens to it under the Reidemeister move? Reidemeister move 1 only involves 1 component, so nothing happens here. There are no relevant ones. Reidemeister 2 may involve 2 components, it might not, but if it doesn't, then it's not relevant. And if it does, again, it's not going to be interesting unless this one is component. Which one?
Component 2.
Correct. If it's component 1, then it didn't go. Component 2 didn't go over. Okay, so if this one is component 2, so it has to be only interesting if this is component 2 and this is component 1. Okay, now if you look at it, it doesn't really matter what the orientations are. I mean, you have to pick some orientation. But whatever the orientations are, in one case, the red one is going from right to left, and in the other one it's going from left to right. So one will be a +1, the other one will give you a -1 contribution, there will be no change. Okay, now here we don't have to go through all the cases, because there are 3 crossings. And if you look, there are similarly 3 crossings on the right-hand side. And each crossing on the left-hand side, there's a corresponding crossing on the right-hand side of exactly the same components and exactly the same orientations. So whatever contributions they are, 0, 1, or -1, well, here will be the same there. When you add them up, it will stay the same. So that's the end of the proof. Now it's invariant. Now we can use it. And now we can actually talk about these things. Okay, so before I answer this question, there's an amazing formula of Gauss, which it's combinatorial formula, the same invariant, definition number 2, in terms of of an integral. So if you represent k1 and k2 as functions of two variables, r1 is the parameter s, and r2, the not 2, with parameter t. So you take the following, you take the difference, which is a non-zero vector since the two knots do not intersect, divided by the norm cubed of the difference, and then dot this with the derivative of R1, yes, which the derivative of R2 at t, the s dt, over whatever. If you're going 0 to 2 pi, you go 0 to 2 pi, whatever other range you have to feel like in your parameters. So the amazing thing is, this is an integral. You wouldn't expect an integral to give up. It's not quite thinking that. You wouldn't expect an integral to give an integral answer, an integer answer. In fact, the answer is an integral multiple of 4 pi. So this has something to do with anyone who happens to be rather advanced. You can define a map from a pair ST to this vector, which is the difference between a point on one knot and a point on the other knot, divided by its norm, so it's a unit vector, and that will give you a map from S1 cross S1 to S2. And its index, so only if you're a senior, you would possibly know what that means, and probably know one. Its index is the linking number. But anyhow, it's an amazing differential geometric expression that gives a result which is an integral multiple of something. Okay, yes?
But like by definition, right, the linking number is an integer, right?
Well, that's that definition.
Sure,
But
like,
it's
if you like analytically solve for it, it's just clear that it has to be a definition.
Yes,
Or it
well,
has
it's
to
true.
be-
So I guess one way of proving this is to show that if you make small changes in either of the curves, it's invariant. And then you make the curves very close to the plane, so you make them both on the plane, and one goes above and one goes underneath, but very, very close by. And then you see that the only interesting contributions to this are from when they're very close, and then you'll see exactly what the contributions there are. But it's still not so. You're right. Okay, and for this, by the way, you can now see what happens if you change 1 and 2, what's going to happen. This will change sign. This will also change sign. So it won't change sign. Okay. You could have seen on the other one too, but it's not so obvious on the other definition, because here we're talking about where 2 goes over 1, here we're talking about where 1 goes over 2. They're completely different crossings. So it's not really obvious that they have to be the same number. Okay. So that's a linking number, which is invariant, so it can help to distinguish something. We can distinguish this. But for example,
I have a question.
yes.
This might be a leap, but like, is that anything like the Gauss-Bonnet term for that specific?
Yes. You're very good.
Yeah. Okay.
Yes.
Cool. Yeah,
Yes, exactly. That's the idea. Yes.
Yeah.
Now they've also got a map that's from S2 to S2, a Gauss map, and it's the index of that. Yes, exactly. Very good. Okay. So this is a link. The white-head link. Well, link with 2 components. Its linking number, you calculate it this way, you'll find it 0. But you'll also find it's not trivial. You can't separate it. You can't pull the pieces apart. So certainly the linking number isn't enough. And if you know about Borromean rings, so they're three component link. Link, which is such that not only are the linking numbers of every pair 0, but actually if you ignore any component, the other 2 components really fall apart. It really is an unlink. not sufficient. Okay, so what about something that's really not invariant? The first one that gets anywhere is a three-coloring number. So this will be defined, yeah, we're going to use diagrams. Start with a diagram. Take over crossing arcs. So, I'm going to take my example here. So over crossing arc means it's limited when it goes under. So we have 3 over crossing arcs here. So we're going to take a set of over crossing arcs in the diagram and map it to modulo 3. So we like this 3 symbols 0, 1, 2. And we're going to do it in such a way, this is going to be called a free coloring, if at any of the 3 crossings, so any of the 3 crossings, there are going to be 3 arcs involved. They may actually be the same, but still there are 3 arcs involved. It's going to have to be such that the values, these numbers 0, 1, 2, that we assign on these 3 sum to 0, modulo 3. So it's just a fancy way of saying that either they're all the same or they're all different. And then the 3 coloring number will be the number of 3 colorings, the number of sitters. Okay, I'm going to write it M3, and this is the 3 coloring number. So for example, on the trefoil, we have we could colour this way, this way, and this the third way. Okay, so that's now at every crossing, all 3 colours are mentioned. Or we could colour them all the same way. So we colour the whole knot with the same colour. So how many ways, how many 3 colourings are there for the trefoil? How many of them like this? And how many like this? Well, the answer is symmetry, but we don't have to get. Okay, so there are 9, okay? On the other hand, if I took an unknot, then how many colourings are there? 3. Yeah, okay. That's only 1 arc, yes? So they're different. Okay, but I haven't shown it's invariant. So to show it's invariant, you have to show that the set of 3 colorings on any 2 diagrams that are related by a Reidemeister rule are of the same size. In order to do that, you can show that there's a 1-to-1 correspondence between these colorings on any 2. So for example, if you do a move like this, so it looks like you have 1 arc here and another arc there. This is all 1 arc. This is all 1 arc. Okay, so here you've got I, and the J is also an I, and since these are already the same, then this is also going to have to become the same color. So actually, you have no more freedom here than you did here. Okay, here, well, similarly, you go through this one. So let's say we have, let's call this I, over crossing arc. Let's call this J. This is going to have to be in modulo 3 arithmetic minus I minus J, because the sum of this crossing is going to have to be 0. I, J, this is going to have to be minus I minus J. Now coming into this crossing, we have minus I minus J, I, and so this one has to be, in order to make the sum 0, it's going to have to be J again. Okay, so in any colouring of this piece of a knot, any variable 3 colouring will have to be of this form. And if it is, then we'll map it to the 3 colouring of this diagram, which is I and J. It doesn't have its minus I minus J in the middle, but it doesn't have it. And similarly, you can see for the slide. So you show that the number of crossings is the same, and then this is our first proof, in fact, that the trefoil is not an onset. Okay, but it's certainly not going to distinguish the trefoil from its mirror image. To do that, well, you need something else. So Okay, so this. Will you allow me to go over a few minutes or?
Yeah,
sure. Okay, okay. So, see something. So this is a Kaufman bracket which will lead to the Jones polynomial. So this works this way. Each crossing I will replace by, I will get rid of the crossing in two possible ways. So any crossing, something is going over, something is going under, we can orient it so what I call a slash. This is a slash, a backslash would look like this, but we can turn our heads until it looks like this. So now I'm going to get rid of the crossing. I've got four pieces coming in here, and I'm going to get rid of it by either getting rid of it and joining them up that way, or getting rid of it and joining them up that way. And I'm going to algebraically replace this by A times that plus B times this, where these are different symbols. Now if I do that every crossing, so if I had a knot, then so if I have my trefoil, you do it every crossing. With each crossing, I'm going to get two pieces appearing. Here I'm going to get two. Here I'm going to get two. So when I finish, we'll have how many turns? Yeah. I have 8 terms because each one we can do independently. So we'll have a sum of 8 terms. And what will they look like? Well, there'll be powers of A times powers of B times the diagram. What's the diagram look like? Well, it had no crossings left, so we got rid of them all. So what could it possibly look like? It's closed, has no end, yes, and has no crossings. Circle, or several circles, yes. So it's some diagram, some number of circles. So for example, you can think of this, you're splitting it this way or this way.
Wait, why is it 8 and not 6?
Because each one you can do independently. So if you think of this as being like a little mirror, you can either place a mirror here or a mirror here, and it will bounce off. It's here, it will bounce off like this.
Okay, okay.
Bounce again. So then I can place these wherever I like on here, yes? And then it'll bounce around and get whatever curves we get. So 8 terms, okay? So for example, if we had them all looking like, in the case that we have here, we have them all looking like A. Well, there is a slash. Where is an A? An A is coming down here. So, well, A, then it will look like this, this, this. And when we apply this operation of splitting, well, what will it do? We'll have bouncing around the outside and another one in the middle. Okay, so what will we get from this term? We'll get A cubed times, well, whatever we want to associate with this. So what we will do is if we have k loops, we will associate a term d to the power k minus 1. So for example, this thing will associate with 2 loops, d, and so on. So if you do, I'll just do one more, then I'll write down an answer. So here, if I do an A, and B, if I do A here, A there, and B, so the mirror is down here, now we'll bounce around and see what happens. So the curve would be, when you bounce around, yes, you're going to bounce here, and then here, and then here, and here, here, and here. Oh, there's only one component, yes? So that's going to give you A cubed B. K is 1, so you will take it easy. Okay, so there are 8 of these, and the term, because it was a trefoil, so the term
A squared?
Yeah, it's squared.
A squared?
A squared, yes, thank you. Yes. So, because of the symmetries, A, B, you have a different one, B, B, so there are going to be 3 like this. Then there are going to be terms with A, B, B, and there'll be 3 of those too, and it turns out that that will come with a D. And then there'll be B cubed. If they're all B's, well, all B's would look like this. So what will that do? Yes. So you'll get B cubed times
B squared.
B squared. Okay, so that's something, a lot of expression. But in order for it to be any good for anybody, it has to be an invariant. How is it going to be an invariant? Well, you have to check the right master moves. Okay, so I'll only do one. One is this thing. And on this one, well, this one is a positive crossing, so it will be this way, A times it, or top one here, plus B times splitting the other way. Okay. Now I'll split the top one. On the top one, you have to turn your head, so A will be this way, so it will be A times this one, plus B times this one. Now, here again, A is this way, so it will be A times this one, plus B times something like that. Okay, so I have to count out what we've got. What have we got? We've got things looking like this in various distorted forms, but they're all the same. Namely, we've got A squared of them from here. We've got B squared of them from here. And then we've got this term, which is AB with a loop in it. A loop gives an extra factor of B. And then we've got this one turns in here, which is really this thing, and it's AB. Okay, what do we want? We wanted to have a Reidemeister move that takes this is supposed to be equivalent to this, which means, let's get this. In other words, like this, B equals just that. Algebraically, when is that going to happen? Algebraically, this is going to happen precisely when, well, this is 1 and this is 0. So you're going to need A, B needs to be 1, and A squared plus B squared plus AB is 0. Okay, so that means that B is A inverse and D is minus A squared minus A to the minus 3. Okay, so you can go and you can check the third move and you find that also it will be satisfied under these conditions. So we've now got one parameter. Our invariant is now not a polynomial in three variables, A, B, and D. It's only one variable. So you work it out and you get an answer. In this case, minus A to the 5th, minus A to the minus 3, plus A to the minus 7. That's what happens if you substitute what we do. So it turns out, as I said, it's invariant under moves 2 and 3. It wasn't quite invariant under 1, but it's almost invariant under 1. Under 1, it turns out that it just scales. So under this thing, if you twist it this way, it'll multiply by a factor. And if you twist it the other way, it'll multiply by another factor. And that's all. So what that tells you is that the maximum that can happen if you go through many moves is to multiply by a power of minus A cubed. For the trefoil, we got this. For the unknot, well, the unknot, there aren't any states. There aren't any terms. You'll just get one. If you don't have a loop, you have a loop. This is clearly not a power of A to the minus 3 or minus A to the minus 3. So it's not the unknot. But we already proved that, so what? But you can get something out of this immediately, and that is that if we take a mirror image, what was the definition? The definition at the beginning was this line here. Take a mirror image, what will happen? This slash will go to a backslash. You get a backslash, we have to turn our heads. We turn our heads, we turn these things, this will turn into this, and that will turn to that. In other words, A and B will be interchanged. But we saw that B is actually A inverse. So when you take the mirror image, this polynomial will change A to A inverse. Now, if you change A to A inverse here, that would be what you would get to the mirror image. You can also see that polynomial is not a multiple of, not this, times the power of minus A cubed. And therefore, the trefoil is equivalent to the mirror image trefoil. Okay, so you can actually correct this so that you don't have this strange change. You correct it by some factor called the and then you take that times what we just discussed there, which is the Kelvin bracket. And this is the Jones polynomial. So this is actually an invariant. If you want to write it in terms of the usual variable that people use, Q, the relation is Q is A to the minus 4. So this is the Jones polynomial, and it's a really interesting polynomial because it's on the one hand pretty easy to compute, and on the other hand, its structure is somehow not coming out of classical topology. So I didn't really talk about classical topological techniques. I was much more in combinatorial techniques. But the classical topology of the early 20th century didn't manage to come up with this polynomial. It came up with similar polynomials, which didn't really distinguish the Fresnel from its mirror image. You could if you worked a little bit, and the main importance of the Jones polynomial is not actually its distinguishing power between knots, but the fact that its definition can be related to so many different areas. In fact, we really haven't seen today. The way I just constructed it over there in terms of the bracket, Kauffman bracket, is a sum of terms. It's related to a partition function in statistical mechanics. It actually has a much deeper connection with statistical mechanical models than just that. It's connected with, it's a special case of things that can be generalized and come from quantum groups. It's connected to invariants of three manifolds. It's connected, the original way that Jones came upon it was by von Neumann algebras. Really a host of different connections with other fields that just came out of this one new discovery. So I think that's something that makes it really rather interesting. And perhaps, just to finish, going back to the vortex theory of atoms, there was the idea that maybe there was a connection between knots and atoms, somehow prime knots would correspond to atoms, and if you put two knots together, so that's something I didn't mention, if you take two knots, there's a way of joining them. It's a bit like multiplying numbers. You can join them together, and you get something that's a composite knot, not a prime knot, but that was supposed to correspond to molecules. So there is some connection which we don't really believe in the vortex theory of atoms anymore, but the underlying idea that knots tell us something about space has recurred. The theory that's related to not polynomials, the Jones polynomial is related to topological quantum field theories, and I think it really is the mathematical theorem that any connected compact three-manifold can be expressed as surgery around a knot. So indeed, to some extent, if you want to look at three-dimensional worlds, then knots really contain all the information there. So perhaps that's one of the reasons why knots are so interesting. On the one hand, they sort of like prime numbers, they're number theoretic things, but on the other hand, they contain all the geometry. You can use all the geometric tools you might want to use. And on the third hand, they're connected with algebra in many different ways. It's a very interesting topic. Hope you enjoyed it.
You talked about the stick number of torus knots where n was less than 2n. I was wondering what's known about the stick number for.
In other cases, I don't know. I don't actually know that proof either. I just came across it in a nice fact. Yes.
Okay.
Yes. So there are interesting inequalities between many of these different invariants. For example, between the stick number. Yes, there's an inequality between that in the general case and the crossing number. So on one hand, something linear and maximal balance 3 halves, and crossing number plus 1. And on the other side, there's something square root of 7 plus 1. It's something complicated. And that's true of many of these invariants. Yes. Yes.
Can you just clarify how you distinguish A from B for the
No, yes. So it's just a matter of every crossing you can turn so it's in the slash form. And if it's looking like a slash, then A will be with a vertical mirror, and B will vertical mirror, and B will be with a horizontal mirror.
So you have to turn it into that position first?
Yeah, well, you can turn your head so it is in that position.
Okay.
So here, yes, the slash is here, so this is A. And here, you have to turn it, so the slash is here, so this is A.
Anyone else? those people who like kind of walked in as the talk was going on, please like sign in on the sheet over there so that we know like how many people were at the meeting. And